You hear me? Okay, sounds like it. Cool. Hi, my name is Ben, and I'm here to talk to you about operating your systems. You'll have to sort of accept my apologies. This isn't a monitoring specific talk, but I hope you'll get something out of it regardless in your capacity as an engineer, as an operator, as somebody who deals with this kind of stuff. First, the obligatory about me hiring thing. I work at a company up in Seattle called ID Softworks. It's a very small startup. We're doing some kind of fun stuff. If you're at this conference, we probably want to hire you, so come chat with me afterwards if you might be interested. Prior to working at ID, I spent about 3 years working at a company called Cloudant, working on reliability and operations. Cloudant sells a distributed database as a service, and it was really a formative time for me in a lot of ways. When you spend that much time really thinking about operating a single service, you have a lot of time to think really meta thoughts about what you're doing and how to make it better, that sort of thing. And so that kind of motivated me to come and try to share some of that here with everybody here, right? So I want to talk about how we operate systems. Still filing in here. I want to talk about how we make our systems reliable, day to day, month to month, year to year, and how do we think about those systems? How can we get better at thinking about and understanding our systems? I think there's been enough talk about John Boyd today that it's sort of inarguable. It's the way that you think about your systems and how you build good mental models about your systems is really important in helping you understand them, helping you make good operational decisions about those systems. But I think there's a problem there because as engineers and as operators, we're not professional educators. We don't know how to do this sort of thing very well. We take a default approach, right? We do whatever comes first, whatever comes naturally to us. And it turns out that's not very good in the end. Like just handing somebody a pile of documentation as a strawman case is not a good way to teach somebody about that system. And so it's worthwhile to really think about how we can do a better job, I think. So back to my background a little bit. When I joined Cloudant, we had about 5 engineers. And all 5 of them sort of came from this open source community that the project was forked from. So they'd sort of gone from working on the project in their spare time to just getting paid for it. They didn't really need to learn a whole lot about the system, right? They knew it. I was a little bit different. I'd never worked on a database before, let alone this particular database. And when you're in a startup and you're moving that fast, there's nobody there to hold your hand, you're working in a distributed team, you don't have a whole lot of ways to learn about the system in a very easy fashion. I was really on my own to try to become effective at this. And somebody who's interested, really worked on reliability and operations, I had to really understand the system pretty deeply in order to do my job effectively. On the plus side, we had way more customers than we were equipped to deal with, and the system broke all the time. It was terribly unreliable. And so I had a lot of learning experiences and opportunities, and I'll kind of come back to that later on in the talk. If you fast forward a couple of years, though, and sort of the company became much more established, we were successful, we were eventually became part of IBM. And we had maybe 25, 30 engineers. There was documentation. I didn't have to take overnight pager shifts. There was a lot more help for people that were coming on board and coming into our operations rotation. And there was a lot more help for them to try to understand the system and try to do a good job. And I assumed that this help, this documentation, this more engineers just around knowing the system would make for a more powerful learning environment for those new engineers. It turned out I was really wrong, right? Time and again, I saw smart, talented, eager engineers really struggle to try to figure out how all these things fit together. Because it's operating distributed databases that are sort of not really super awesome can be challenging. And I recognized that they had hard problems in front of them, but I was surprised at the challenges that they faced, and how hard it was for them. And so as somebody responsible for reliability and operations, this was really troubling for me. I really tried to think hard and really tried to reach out sort of across disciplines to try to understand how we could do a bit of a better job. Right? So I kind of went off the deep end on this a little bit. I have a stack of books maybe this high about this various educational subjects. I maybe only read half of it. And I've come across a lot of ideas. Some of them resonated with my existing experience. Some of them maybe didn't. Some of them, showed me new ways to kind of approach the problems I was facing. And the big idea that I kind of want to come here and share with you today is this idea that the way in which you experience your systems, the way that you interact with your systems is, I think, incredibly important to coming to a good understanding of how those systems operate, and ultimately to make better operational decisions about those systems. Okay. If you can find ways to have more powerful experiences with your systems, you'll come to understand them faster, come to understand them more deeply, and be able to make better decisions. And that's kind of fuzzy, and it's been hard for me in the past to really kind of try to describe this to a lot of people, especially engineers who want things very concrete. From my point of view, it's a little bit more of a collection of patterns. It's an I know it while I see it sort of thing. But I think there's ways to approach it and ways to sort of draw analogies that can kind of illustrate what I'm talking about. And it's a hard problem, though. It's hard to find that sort of right balance. Right? So luckily, there's somebody out there who's both much smarter than all of us, as well as has spent a lot of time thinking about this already. Seymour Papert is a mathematician at MIT. He helped found the AI lab and the media lab. He's a super influential guy, and he's probably best known for inventing a programming language called Logo. And for sort of the purposes of what I want to talk about here, I want to kind of dive into that bit of his work a little bit. The Logo program is a series of commands for directing a robot called a turtle. A turtle is a machine that sits on the floor, it has wheels, a direction, it can move forward and back, turn left and right, and it has a pen that it can use to draw on whatever surface it happens to be sitting on. The commands that the turtle responds to are straightforward. Something like move forward 10, move forward 10 units, right 90, turn right 90 degrees, that sort of thing. Right? Young children, generally like elementary school age children, they use the turtle and they use Logo to explore relatively complex mathematical concepts, differential geometry and things like that you wouldn't normally teach an elementary school child. And they do this by writing programs to direct the turtle to do something like maybe draw a circle or draw a house and that sort of thing. Right? So as the child's first introduction to some pretty complex mathematical concepts, I think the turtle's really fascinating. I certainly was not taught any sort of geometrical concepts when I was 6, when I was 7. I was learning arithmetic and that sort of thing, right? And so I thought this was really both interesting and kind of like maybe worth drawing a lot of kind of some inferences and trying to figure out what we can learn from it. Papert, the author, described the power of learning via Logo through an analogy with learning a foreign language. He pointed out, and I think a lot of people have this direct experience, for somebody trying to learn a foreign language like French in a United States classroom, even when the teacher is a native French speaker, they'll often struggle, right? Like it's very difficult to sort of take that experience and have it in a classroom setting. But if you take that same learner and you take that learner and place them in France in this sort of immersive environment, they'll often be able to pick up the language no problem at all, right? It's sort of innate in the types of experiences you can have with French when you're living in France, right? Analogously, Papert describes learning math via Logo as like living in math land, right? It's like learning French in France is like learning math in math land, right? He uses words like fumbly and personal and interactive, immediate feedback, that sort of thing to describe what it's like to learn Logo via mathematics, learn mathematics via Logo, and contrast that with the sort of more traditional learning experience in a classroom. Right? Furthermore, for the child, the turtle, this robot, is relatable in a way that most mathematical abstract concepts aren't, right? The Euclidean point is just this very, very abstract thing for a 6 or 7-year-old to understand. But the turtle has a position in space, and the child can touch it, right? It's right there on the floor. It also has a direction that it's facing, just like a child, right? It's something that they can really physically identify with because it's part of their world. Right. The children are encouraged to physically step through their programs as they debug them. Go out into a field, go forward 10, right 90, and try to understand the nature of this mathematics through themselves. Right. Papert appropriated this term syntonicity from the psychology literature to describe this notion of relatability. The turtle is really firmly related to the learner's existing notions of themselves, of their bodies, of their world, even of their intentions and their desires and their goals and that sort of thing. So, and then they can take this relationship, this syntonicity, and they can leverage that relationship in exploring this really new abstract problem domain that they didn't previously understand, right? So the exploratory nature of Logo and the syntonic nature of Logo encourages the learner to engage in a conversation with this world, with this abstract world. And these conversations are really the focus of Papert's theory of knowledge. These are really, I think, powerful ideas, and what I want to understand is how sort of we can translate these to our world of web operations, and how we can translate them to sort of gain leverage in understanding our own systems. How do we find ways to have syntonic experiences with these highly complex, highly abstract distributed systems that we're either building ourselves or that we're tasked with operating, that sort of thing? How do we build something like OpsLand, right? I think this is an interesting challenge. And I don't think I have a whole lot of answers. I do think I can try to illustrate it with some examples, and hopefully kind of point towards what I'm trying to get at and what I'm trying to communicate. So first off, an anti-example. I think that tuning garbage collectors in the JVM is really kind of a crappy experience. I think it sucks. I don't have a great mental model of how the heap allocations, the Eden space, the young generation, tenure generation, perma generation, all these sort of things, this whole system fits together. For me, it's really challenging. I think it could be easier. I'm not suggesting that it could be made easier in the context of JVM, but I think there are reasons that for me it's challenging. For one, it takes a really long time to get feedback out of the system. You know, if I'm working on a tuning and garbage collector, it might take 5 minutes, it might take 20 minutes, it might take an hour for my system to actually demonstrate the type of failure that I'm trying to correct. And I can't, as an operator, make any changes to configuration that might correct that problem without restarting the system. And then I'm back to waiting that 5 minutes or that 30 minutes or that hour, right? I don't have any notion of interactivity. It's like having a conversation with somebody on Mars, for example, right? Like you can't really communicate with the system in any direct way. Furthermore, you have a really small window into what the system is actually doing. The tools that are immediately available to you, Visual VM maybe being the most powerful one that I can think of off the top of my head, stack dumps, verbose GC logging, those types of things. They're very limited. You can only look at the things that the JVM tells you can look at. There's no real freedom. There's no fuzzy personal exploration here like Papert describes with his Logo systems, right? And I think that's really unfortunate. I think for me at least, if I had more freedom, if I had more opportunities to explore, I could do a much better job at understanding the system and ultimately do a better job at making the JVM-based systems more and more effective, right? As sort of a counterexample to that, there's the graphite system. So if you've used graphite, particularly in the Carbon cache, you probably know that sometimes fiddling with number of writes per second, number of creates per second, cache size, and all these types of parameters that Carbon cache provides you can be a little bit touchy. If you get it wrong, badly wrong, then you're sort of going to lose data. And if you need to make changes, it's a cache, right? And the only way to scale the system is to keep a lot of memory in cache, so you put a lot of data in cache, so you're going to lose data if you'd have to restart the system to change your parameters. Luckily, there's a way out of this. There's a nifty little hack built into Graphite called the manhole. The manhole is an SSH, a Python REPL delivered over SSH into your running Carbon cache system, right? So if I SSH into my Graphite manhole, I can actually configure my system on the fly. And I can change configuration parameters and observe how they affect the system in real time. And I'm not just limited to that particular configuration parameters, right? I can explore the system more deeply. I can look at any of the data structures involved in the system. I can inspect them, I can change them, I can explore how the system operates through a pretty familiar interface. For me, the Python REPL, right? And I think that's pretty interesting and pretty powerful, especially when you compare it to something like the JVM garbage collector. On the other hand, though, it's only really half of the story, right? It's powerful, but it really does, I think, lack this notion, at least for me, this notion of syntonicity, right? I can logically understand the carbon cache, but I think that's only because it's a very simple system. You know, it has an input, it has some memory reading, data structure writing and stuff in the middle, and then it has some outputs, these files that it's actually writing. But there's no distributedness, there's no real concurrency or anything like that. It's a very, very simple system. So I personally, and I imagine most of the people in this room, can leverage their existing experience and their knowledge of these types of systems to understand carbon cache from like a strictly abstract logical fashion. But for me, at least, when I try to take that same approach to understanding a much more complex system, say, let's take Zookeeper, for example, something that's come up today, it's completely beyond my abilities. Like, I need more powerful levers, right? And I think that's missing in this case, right? I think it's okay because it's a simple system, but I think it's missing. So some of you may have seen this coming if you know my background and know what I've been talking about and maybe have some experience with airline. But I think the airline programming language and programming environment exhibits a lot of these things that I've sort of been exploring, that I've been talking about. Erlang was designed back in the 1980s at Ericsson for developing highly reliable telephone switches, stuff that can't really go down, right? You're running emergency broadcast services on it, for example. It was originally implemented in Prolog. These things kind of show. It's a little bit wacky, and it turns off a lot of developers from the start. But it has really, I think, a certain elegance to it. Once you really get to know it. And its focus on building reliable distributed systems has some interesting consequences once you're actually involved in running a system, okay? In my opinion, it's from my experience, it sets itself apart in the leverage it gives in understanding these complex systems. And it's the closest thing that I've experienced to what I would describe as an ops land, right? For one, every airline system has a REPL. It's built in, it's standard. You don't have to wait for some clever fellow to sort of implement this SSH delivery of a REPL into your Python program. It's just built in. Anyone familiar with airline can sit down at a React node or a CouchDB node or a RabbitMQ node and start exploring. You have a lot of support from the platform in a standardized way, right? And because it's built in, because the platform supports it, there's a lot of stuff built into your standard library that you wouldn't see in other programming environments. You have debuggers, you have tracers, you have deep introspection capabilities that just aren't there in, say, your Python or your Ruby or your Go, that sort of thing, right? You can take stack traces, you can inspect the garbage collection or heap allocation patterns of your running system, at will. But you can also look at the code that's executing. You can change the code that's executing in your running system without sort of making any real changes to your system. And that's not limited to user-focused code. That's any code in the system. I can change the runtime at runtime without any real penalties. It might blow up the system, it's true, I've done that in the past once or twice, but by and large, you have a great deal of freedom to do this sort of stuff, and it's really eye-opening when you have the platform backing you up in that fashion, you have the community backing you up in that fashion, because everybody does it, right? It's a great lever into understanding complex systems. And that might sound like a little bit of sugar on top of what you might experience with the Graphite REPL, for example. But I think there's more to it from my experience. For me, interacting with an airline system is a very deeply symptomic type experience. The fundamental unit of computation in Erlang is a process, right? It's simple, it's sequential. The only way it can communicate with the rest of the world is by sending messages and receiving messages, and everything, data structures are immutable. It's all this sort of functional language, gobbledygook stuff. There's really no complexity to these processes, though. They're very easy to understand by and large. So you have an airline system, and the actual computation is happening in these hundreds, maybe thousands, maybe millions of individual processes. And you have all these deep introspection tools, and you can use those tools to look at an individual process. The more important bit here, the more important thing about these processes, at least for me, is that these processes, by and large, the important ones at least, have names. And they have a little bit of state that they maintain, and they have autonomy. And then so for me, as a human observer, trying to understand a system, trying to debug a system or something like that, I naturally attribute a notion of identity to these processes, right? I think it's something like an inevitable ape-brain response to being presented with this situation where you have all these things sort of operating on their own, and you can talk to them as if they had a name, they were your buddy, right? For me, like, the processes become, in a CouchDB system, for example, these processes become like old friends. Logging into a CouchDB REPL is like dropping into a familiar bar. I know everybody's names. I can check out on, what Couch server is doing, who it's been chatting to lately, is it overworked, how are things going, that sort of stuff. It's very different than interacting with a system that's maybe more data concurrency driven. A Java system where you've got these executor frameworks and that type of thing, where there's a little less concreteness about the identity of these processes. For me, in my experience, I think this is really familiar, very similar to how children interact with their world, relating the mathematical concepts to their bodies via logo. I'm able to sort of relate to these abstract distributed system concepts through interacting with my airline system because it has these deep notions, because I can talk to it, because the units of computations have names and really, for me, have deep identity. And I think, from my experience, it's a lot more challenging otherwise. And it's not something that maybe gets talked about a whole lot, but I think it's worthwhile. I think it's a valuable addition to my toolkit as an engineer and as an operator, somebody who's trying to deal with these types of systems. I think it really makes for a very deeply powerful operational experience. So I went a little faster than I expected, but I hope that some of you can relate to what I've shared here today, at the very least. And at least I've encouraged you that you should think meta thoughts about your systems and about how you think about your systems and how you learn about your systems and how you teach other people about your systems, because there's value in that. The people here at this conference are the leaders by and large, in our organizations, and we're the ones that have to sort of drive new thinking into our organizations, right? I'm not trying to encourage everyone to rewrite their systems in Airline, though I would not totally complain. But that's not totally the point. My point is to try to encourage you to open your eyes to some new ideas and to some things from other disciplines, right? I hope some of you disagree with me. I certainly know Dijkstra would disagree with me. He hated any sort of anthropomorphization in computing. And I'm totally aware of this idea that when you craft a new perspective to view the world with, there's a risk that you might try to view everything from that perspective. And I'm aware of that risk, and I think I've tried to temper that in how I think about these types of things. But at the end of the day, there's a lot of systems out there, and there's a lot of things that we have to learn. These systems break all the time. They're very complicated. I often break in new and unexpected ways, and everybody here is familiar with that, right? But we all owe it to ourselves as professionals to try to do the best job we can, to learn about these systems, to understand the systems, and to teach about them so that ultimately we can deliver more reliable software, right? That's it. Thank you.